posters. We wanted to work very hard. So the senior dignitaries in the three-piece suits and so on came in to the lab, and we left the lights off, and everyone continued to work. And I made them keep their voices down and talked to them rather in a hurried way, and then sort of shuffled them out the door. And they all had a slightly puzzled look on their face, because it probably had never happened to them before in the history of being a visiting committee, that they were treated with as little pomp. And later I actually met one of the guys who said, I suspected something was up that day, because otherwise you never would have dared to do that.
June the 5th, 1995, turned out to be a big day in the history of physics. They had finally made what Einstein had predicted 70 years before, a Bose-Einstein condensate.
Our first reaction was, wait, we got to be careful here. Let's think of all the different knobs we can turn, checks we can make, and so on, to see if this really is Bose-Einstein condensation.
Condensate is sort of like a vampire. If the sunlight even once falls on it, it's dead. And so its realm is the realm of the dark. But we can take pictures of them because we strobe the laser light really fast, and even as the condensate's dying, it casts a shadow, and the shadow is frozen in the film.
Wyman and Cornell created the first Bose-Einstein condensate in a cloud of just 3,000 atoms of rubidium, the first in the universe, as far as we know. They had reached a temperature of 170 billionth of a degree above absolute zero.
One of the first things you need to understand about Bose-Einstein condensation is how very, very cold it is. Where we live at room temperature is far above absolute zero on this scale. Imagine that room temperature is represented by London, thousands of kilometers from here. Then on that scale, if we imagine right here where I'm standing in Boulder is absolute zero, the coldest possible temperature, then how close are we to absolute zero? If we think of London as being room temperature and right where I am is absolute zero, then Bose-Einstein condensation occurs just the thickness of this pencil lead away from absolute zero.
Within weeks of the Boulder Group's success, Wolfgang Ketterle produced an even larger condensate from 10 million sodium atoms. At last, quantum mechanics was more than just theoretical mumbo-jumbo. It was something that could be seen with the naked eye. Wyman, Cornell, and Ketterle shared the Nobel Prize for Physics in 2001.
One of the things the Nobel Prize means, and the ceremony means, that everybody remembers Eric's the person who forgot to bow to the king.
There was a breakdown of protocol on my part. There was no excuse because they actually drill us. It's more like you have a series of rehearsals practicing how to bow to the king, and I somehow managed to bollocks it up at the last possible moment. And I thought maybe, Carl, who came after me, would make the same mistake, and then no one would figure it out. But no, he was perfect.
I heard about the Nobel Prize when I was woken up by a telephone call, which was at, I think, 5:30 in the morning. So you wake up, you go to the telephone, and somebody tells you, congratulations, you've won the Nobel Prize. You're still tired, your brain is not fully functional, but you realize this is big, and what you feel is pride for MIT, your collaborators, for yourself. It's wonderful to see that your work gets recognized and acknowledged in this way.
Like any great adventure, the pursuit of science offers no guarantee of success. But for the godfather of ultra-cold atoms, persistence eventually paid off. After 20 years of struggling to obtain a condensate in hydrogen, Dan Kleppner finally succeeded. For a few fleeting moments, his dream came true.
Of course, we were delighted, and I think everyone was delighted, because we'd been working on it for so long. It's kind of embarrassing to have this group which helped start the work and was working away there fruitlessly while everyone was enjoying success. When we got it, everyone was happy.
To see that an effort which lasted for 20 years, which took so much patience, frustration and tenacity, to see that succeed is just emotional, it's liberating. I will never forget this standing ovation which Dan Kleppner received at the Varenna Summer School when he announced Bose-Einstein condensation in hydrogen.
Everybody just got up and gave, it was sort of like an opera where everybody just cheered and people were crying, and because everybody realized that they had finished the race, but too late, and it wasn't going to work out, but in some sense they had really stimulated the whole field, so it was a very moving moment.
For the pioneers who had realized Einstein's dream and created condensates, it was the end of an extraordinary decade of physics. Now there was a new challenge: to work out what to do with them. At Harvard, a Danish scientist, Lina Hau, had the idea of using a condensate to slow down light.
We all have this sense, light is something that nothing goes faster than light in vacuum. And if somehow we could use this system to get light down to, to a human level, I thought that was just absolutely fascinating. It is actually very odd. It's also extremely odd to a lot of my colleagues.
Lina Hau created a cigar-shaped Bose-Einstein condensate to carry out her experiment. She fired a light pulse into the cloud. The speed of light is around 1 billion kilometers per hour, but when the pulse hits the condensate, it slows down to the speed of a bicycle.
So light pulse might start out being 1 to 2 miles long in free space. It goes into our medium. And since the front edge enters first, that will slow down. The back edge is still in free space. That'll catch up, and that'll create that compression. And it'll end up being compressed from 1 to 2 miles down to 0.001 micron, or even smaller than that. You could say, well, gee, it's easy to stop light because I could just set a laser beam into a wall and I would stop it. Well, the problem is you lose the information because it turns into heat. You can never get that information back. In our case, when we stop it, the information is not lost because that's stored in the medium. And then when we have time to revive it, the system has all the information to revive the light pulse and it can move on.
One day, ultra-cold atoms will probably be used to process information, but quite how is hard to predict. Sometimes the promised benefits from a scientific breakthrough take a long time to emerge. Many predicted that by this century, energy-saving superconducting power lines and maglev bullet trains would be crisscrossing the continents. Perhaps now, as world energy supplies dwindle, these technologies, once seen as uneconomic, will start to take off. Now it is the quantum nature of the cold frontier that has captured imaginations. Supercooled quantum devices are mapping the magnetic activity of the brain. And cold atoms are being turned into quantum computers.
As a quantum mechanic, I engineer atoms. To make a computer out of atoms, you have to somehow get atoms to register information and then to process it. Why build quantum computers? Because they're cool, it's fun, and we can do it, right? I mean, we actually can take atoms, and if we ask them nicely, they'll compute. That's a lot of fun. I mean, have you ever talked to an atom recently and had it talk back? It's great, learn to speak atom and the atom speak back, that's great.
So the first thing we're going to do is we're going to set up
The quantum world is, and the world of the very small, it's like an exotic wilderness that you've never been in before. and things you wander in, and everything looks strange, and you see things that you've never seen. But if you really want to see what's going on, then you've got to be quiet. So if you go into the wilderness and you're going, blah, 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 then you're never going to see things, because all these exotic phenomena are going to know that you're there, and they're going to stay put, and they're not going to come out. So if you make a lot of noise, that's bad. Now, at the quantum level, at the microscopic level, heat is noise. So if you want to see these strange and exotic effects, you have to be quiet, very quiet. There can't be a lot of noise, and that means you have to cool things down. Yes, look at that, that's beautiful.
Unlike ordinary computers, where each decision is based around a bit of information and is either a 0 or a 1, in the quantum world, the rules change.
At first glance, a quantum computer looks almost exactly the same. But quantum mechanics is weird. It's funky, okay? It's weird.
When you do quantum computing, you want to make this weirdness work for you.
So now let's look at our quantum bit, or qubit.
And a qubit can not only be a 0 or a 1, it can also both be a
0 and 1 at the same time. It's almost like a form of
And if you
parallel
look at the many
computation,
worlds
but in a parallel
interpretation of
computer,
a quantum
one
computer,
processor does this, one
what
processor
happens
does that.
is
So you have
that
two
your
processors doing this and that.
quantum
In a
computer
quantum
is
computer, you
doing
have only
many,
one
many
processor
computations
that's
all
doing
at the
this
same time.
and that at the same time.
Looks like it's more the tuning. So
Within the giant Dewar flask lies a prototype quantum computer surrounded by its supercooled, superconducting magnet. In the future, quantum computing could be used to predict quantum interactions, such as how a new drug acts on faulty biochemistry, or to solve complex encryption problems, like decoding prime numbers that are the key to internet credit card security. This weird quantum world is part of a new frontier opened up by the descent towards absolute zero. It's been a remarkable journey for scientists into unknown territories far beyond the narrow confines of Earth. On the Kelvin temperature scale, which begins at 0 degrees for absolute zero, the temperature of the Sun is around 5,000 degrees. At 1,000 degrees, metals melt. At 300 degrees, we reach what we think of as room temperature. Air liquefies at 100 degrees. Hydrogen at 20 degrees. Helium at 4 degrees. The deepest outer space is 3 degrees above absolute zero, the coldest place outside the laboratory. But the descent doesn't stop there. With ultra-cold refrigerators, the decimal point shifts 3 places to a few thousandths of a degree. And laser cooling takes it down 3 more places to a millionth of a degree, the temperature of a Bose-Einstein condensate. With magnetic cooling, we shift 4 more decimal places until we reach the coldest recorded temperature in the universe at a lab in Helsinki, 100 picokelvin, or a tenth of a billionth of a degree above absolute zero. So will it ever be possible to go all the way, to reach the holy grail of cold, 0 degrees?
Getting to absolute zero is tough. Nobody's actually been there at absolute 0.000000 with an infinite number of zeros. That last little tiny bit of heat becomes harder and harder to get out. And in particular, the timescales for getting it out get longer and longer and longer, the smaller and smaller the amounts of energy involved. So eventually, if you're talking about extracting an amount of energy that's sufficiently small, it would indeed take the age of the